Okay, welcome everybody. So this is going to be a talk about what's called the Shannon Switching game with N cops. So this is a continuation of the talk that Mindfill gave a little while ago. Um, so the just to review the problem statement, in the normal Shannon Switching game, you have a graph. It can be any graph. In this case, I have a clique, but I'm just gonna delete a few edges here. So we're just going to say you have some graph. And the question is, there are two nodes that like signify a start and an end, and there's a cop and a robber. So the cop is capable of deleting edges like this, and the robber is capable of adding the edges to some kind of like colored set. And the goal of the robber is the robber wants to connect the two colored nodes somehow. It doesn't have to be direct. It doesn't have to be like without cycles or anything special. The robber just wants to connect the two via those colored edges, whereas the cop wants to prevent that from happening. So, like for example, a cop win in this case would look like perhaps like separating, I don't know, separating the graph like this before the robber is able to make any connections. So that's the general Shannon switching game. The cop and the robber just kind of alternate between playing. Like that's the standard game. So like for example, um, actually before I start explaining the end cop game, would anyone like to try playing against each other for the normal Shannon switching game, just on a graph of size 4?
Yeah, I'll play. I'll play.
Sweet. Do I have a second victim?
Yeah, sure.
How about me? Okay.
No,
Ooh.
you go ahead. Go ahead.
All right, Mindfill and Zai.
Thank you.
So I'll say Mindfill will be the cop and Zai will be the robber. So Mindfill, what would you like to do?
I'd like to disconnect the edge directly between 1 and 0.
Right. So you want to disconnect this one first because if you don't, then the robber will immediately take that one and just win the game. All right, Zai, you're the robber. What do you want to do?
Okay, I'll do 0 to 2.
Okay.
Yeah, and 0 to 2.
Mindfill.
Delete 1 to 2.
Okay. Yeah. So again, that's sort of forced because if 1 to 2 isn't deleted, then like immediately the robber would be able to connect that edge and win the game because 0 to 2, 2 to 1 makes a connection.
Yep. I guess I have to do 1 to 3.
Yep.
Yeah.
And I guess my choices are the same, so we'll delete 0 to 3.
Okay.
And then I'll connect 2 to 3.
Congratulations, Zai. So yeah, the robber
Hey!
just won with 4 edges. Sorry, with 4 nodes, with a clique with 4 nodes. So we can start this game on graphs of all different sizes and shapes and stuff. Now, Mindfill in the last talk presented an open problem which said, suppose that we just limit ourselves to cliques, because otherwise the space of graphs is kind of hard to think about. So let's just think about cliques. What is the smallest clique for which a robber will win? So in this case, the robber won with 4. What about with 3? What's going to happen here? Any other quick volunteers, or should I just
Yeah,
I'll
sure.
just play against myself?
Oh yeah, no, yeah.
All right, Beer, here. You're the cop. I'll be the robber. So
I mean,
Anyway.
disconnecting 1 to 0 is the obvious move,
right. So I'll connect 0 to 2.
and then I could disconnect 1 to 2 and win.
Right. So in this case, the cop won with a graph of like a complete graph, a clique of 3 nodes, whereas in 4 nodes, the robber won. So I won't prove this right here, but it should be easy to work out that with 4 nodes versus with 5 nodes, like anywhere above 4 nodes, we should still expect the robber to be able to win. I guess maybe a quick sketch of the proof might look something like just identify that there is a sub-clique, a sub-complete graph of the shape of the previous one in this clique of size 5. And for that reason, now we can the robber can maybe just imagine that this four node doesn't even exist and just follow precisely the same strategy with the first 4 nodes, as we had done with the 4 node graph. Okay, so that's the basic problem, and Mindfill presented on a generalization of this problem called the n-cop problem. So this is a problem where we have multiple cops, or in like another way that you could think about it is the cop is able to make several moves per turn. So um, the uh, the simplest case here, of course, is 2 cops. So I guess I'll maybe open it up once again. Does anyone want to try and make a guess on what the smallest click that a robber can win with 2 cops is, and B, would they like to try playing against my solver?
Yeah, I don't know if I'm volunteering, but I was just thinking like if you have like a 6 click and 6 cops, then the cop could just like remove all the edges to one of the endpoints, and then it's just like
Yeah,
isolated.
that's
So
correct. Yes. Yeah, so in Mindfield's talk, he talked about a paper published by, I think it was Kimberly Wood, um, regarding a bunch of bounds that are known for the answers to this, for arbitrary n. Um, but yeah, that's exactly right. If you just have if you have an amount of cops which is equal to the click size, then it's not going to be possible for the robber. In fact, if it's n-1, it's still not going to be possible for the robber because the cop will just go ahead and disconnect like all 5 of the outgoing edges of the one node. And it turns out that actually you can make the bound a little bit closer than that. But um, that's not for this talk. Go and watch Mindfill's talk if you want to know about those bounds. Um, so any volunteers? Anyone want to guess for 2 cops what the smallest graph is that a robber can win on? Hesitation. Don't be shy.
Well, can we try 7?
We can try
Maybe?
7. So are you suggesting you think the robber will win on this one?
Hmm. I mean, I don't have any more information other than the previous video where they said it could be 7.
Okay,
So
gotcha.
might as well try.
Sweet. All right.
Great
Cool.
guess, man.
So
Great guess.
I'm gonna go ahead and if I can figure out the correct key shortcut, I will try and get you to be able to play against this thing.
Oh, do we have like an optimal player here?
Yep. Yeah, that's what I did here. I wrote a little recursive, like just a little minimax solver
Right.
that figures this out. Uh so sorry, we're playing against 2 cops on a graph of size 7, and Zai, you're gonna be the cop. Um I actually didn't get around to implementing like playing as the robber before this talk. You're the cop.
Oh, right.
Um what would you like to do?
So remove 0, 1.
That's very annoying how it moves like that. Hold on. Okay, 0 and 1 are gone.
Okay, so technically now everything is symmetrical again, so I technically only have 2 options, which is to first is to remove anything connecting from 0 or 1. And the second is just doing random stuff. But I think just removing
That sounds
something
right.
connecting from 0 is better, so maybe just 0 to 3, I guess. 0
Okay.
to yeah.
Okay, so 0 to 1 and 0 to 3. And it's thinking.
So the
Oh.
recursion depth should be like 10 or something? Because
Yeah,
it's removing
it
3 every
should.
turn?
I hope this doesn't take too long. It should be able to. Yeah. Okay. Yeah. Sweet. So Robert adds edge 0 to 2, which is this one, if I'm not
Right.
mistaken. Yeah.
Okay. Everyone, I need your help. Okay, so first I remove 1 to 2. Maybe we take
Okay.
turns removing, so we all play together. Maybe I don't just do it all by myself.
Sure. Yeah. I mean, if you want, I can chime in maybe. Not that I think I have any great intuition about the game. So yeah, 1 to
1 to
2
2
is
is yeah.
definitely necessary because 2 is already sort of in the robber's territory. So we'll go ahead and disconnect that one. I'll say 1 to 2.
I feel like 1
And
to 3 or 1 to 6 is like the move too, because we're gonna want to remove both of those within. Because the move might just be like the robber goes to 6, and then we're in a pretty bad spot at that point.
that seems
So if we could,
sensible. I mean, one thing I like about this little thing that a robot made for me is you can kind of see just visually the distances that things have to each other. So like 1 to 6, like yeah, 6 seems pretty close to 0 and 1, I guess, question mark maybe. It's a very central node, and 1 is also a node that you want to get to. So maybe, yeah, maybe that's a good thing. I'll go ahead and go with that. 1 to 6.
Yep.
Not 1 to 6. Robert adds
I
0
believe
to
6
4.
and 5. Uh-huh.
Okay. Well, so now we definitely have to remove 1 to 4. Anyone else wanna take a go at the harder move here?
I feel like node 5 is still very well connected, so maybe 1 to 5.
1 to 5 might be good. 1 to 5 might. Should I go with it? Maybe I'll just go with it.
yeah, that feels pretty strong. And at that point, there's only 1 to 3 to remove, which feels like we win at that point.
If we go 1 to 5, then the robber will take 1 to 3, and then we
Yeah,
have to
the
disconnect these two.
there's sort of like two classes of moves you can do, right? It's either in response to something the robber has claimed, or simply because the objective honestly is just disconnect U and V. So you either start by just disconnecting nodes from U or V, or you start playing in response. So I think right now there isn't necessarily. Yeah, I think the best thing would either to delete edges from 1 to 3, 1 to 5, or 0 to 5, and 0.
Hold on, because if you delete 1 to 5, right?
Yep.
Yeah, if you
That's a
delete 1 to 5,
necessary win.
yeah,
Yeah,
There's an
it's a
undo button, so
necessary
I'm just gonna
win.
go ahead and do it.
Okay.
yeah,
We can
they're gonna do 1 to 3,
Yeah.
and then after that they're gonna do 3 to 5, and then they win, I think.
Yeah, so we would then have to disconnect these two.
All right.
Yeah.
Then they would take. Yeah. Well,
Yeah,
I don't know
3
what
to
they would
5
take,
gives
but
to connect. So
that's true. Yeah. That is true. Right. So yeah, now there's 3 options here. Okay, so that's no good. So what is this where we were? One more time. Yes, we deleted 1 to
Yep.
4. Okay, yeah. So delete 1 to 4. Now what? Not 1 to 5. What should we do?
Should we delete 5 to 3? I might
I'll
be
go ahead and
insane
try it.
here.
Let's delete 5 to 3. Sorry, I'm forgetting that I have to
I
type into
think
the box.
yeah, they're gonna do 1 to 5.
It says 1 to 3.
Oh. Oh, that's this. Really?
Yeah, because I think
But
if
1 to
you
5 wins on the spot too, I think.
Yeah, it does win on the
Well,
spot.
it's
actually.
symmetric.
It's not
It-
entirely
it's-
symmetric because 3 isn't connected to 0.
Oh,
But
yeah.
okay. So let's go ahead and play it. So
I guess
I'll just go ahead since
yeah.
we definitely need to disconnect 3 to 4 and 3 to 2. 3 to 4 and 3 to 2. Oops. 4, 3 to 2. And now the robber takes 1 to 5. And once again, you can see that it's triply connected to 4 to 0 and to 2. So we've lost. We can. Would you like to? Actually, yeah, we've definitely lost now because Unfortunately, there's no undo button in this program, so I'll just go ahead and say 5 to 4, 5 to 0, 5 to 4, 5 to 0, and Robert adds 0 to 6, and you can pretty much see where this is going. We delete 6 to
But wouldn't 5-2 win for the robber right now?
5 2. Oh yeah, that's correct. 5-2 would immediately win. This my solver unfortunately doesn't find like the shortest win or anything. It just finds a winning move. In fact, it finds the lexicographically first winning move. So 0 to 6 starts with 0, so that is preferred. You're probably right. I wasn't paying that much attention, but yeah, there was probably a much better way.
I guess that just means the robber has like so many ways to victory that it can be a little loosey goosey with it.
Exactly, yeah. Anyway, you guys all see where this is going. We're not going to win this. So like at this point, you can probably tell that there is robber added 0 to 6, and now we have 2 deletions. Now 2 to 5 would win for the robber. 6 to 3 would win for the robber. 6 to 5 would also win for the robber. So like, there's no way we're going to win. We can just go ahead and pick 2 of those nodes. I'll say 2 to 5. We'll delete 2 to 5, and like 6 to 5. And yeah, robber takes 3 to 6 and wins.
I mean,
We
strictly
ended up with
speaking,
Clique,
if we were the robber and won, that would have proved that the robber can win, but we haven't really proven anything with this exercise, except that it's difficult to prevent the perfect player
That's
from
correct.
winning it, at least.
Correct. So would you like to instead start with a case in which you think that you can beat the optimal solver? Want to go one down with 6 and see if we can beat it? Anyone wanna? Here, I'll go ahead. So we know we're gonna disconnect 0 and 1.
Delete 1 and 2.
Delete 1 and 2. Okay. Robber adds edge 0 to 2. Now what do we want?
It's like a Moser spindle.
A what?
Oh,
A
it
Moser
is.
spindle? What's that?
Wait, that. I remember learning about that from the Hadwiger-Nelson problem. I think it's like it's hard to describe. It's like 4 triangles. Well, okay, we don't have to worry about that right now.
Okay. I'll Google that later.
And here we can delete 1, 4, and 1, 5, right?
We'll delete 1, 4, and 1, 5. Okay. Robber adds 2, 5.
Oh, yeah.
Is
Okay,
that
that's pretty
self-evident
stupid of the
here?
robber. So we can just disconnect 1 and 3, and we win. It also, if it doesn't know what to do, it picks randomly. So it seems that we were winning. Let's go ahead and walk through what happens if we go ahead and do 1 to 3. So if we connect here, then
Then we have to do 2 to 3 because
we
that.
have to
like-
disconnect these 2.
Yep.
Now this is a cut that we could make on the next turn to disconnect like both 5 to 3 and 3 to 4. So the robber will have to take one of those. And now at this point, we have to disconnect 0 to 4 and 2 to 4. And now these two cuts through like either this slice or this slice are miai, as a Go player would call it. So that is like if the robber plays on one side, then we play on the opposite side. And by symmetry, it works the same way. So okay, so we beat the optimal solver for 6. So all we know now is that the answer is greater than 6 for what is the smallest robber win. Now I'll go ahead and maybe I'll go ahead and spoil the answer, because as someone noted, I forgot who, there's no way that we can actually prove by playing and winning. No, sorry, by playing and losing against the computer against 7, we can't actually prove anything. Um, so it beat us once. So maybe we just played terribly, but maybe it's actually impossible for us to beat the robber in this configuration. So, any final thoughts before I spoil the answer?
This feels like an available paths thing. Like I probably missed out a lot on missing the first talk, but it feels like there's something there with like the forced moves and how many remaining paths that exist. But I'm not smart enough for that.
I don't know either. Maybe you're right. Once again, my solution here is just brute force search. So there's no
I feel
clever graph
like
theoretical arguments involved.
in this case, I feel like no matter how fast we try to cull the edges, we end up having a 5 click, which is somewhat covered enough by the robber so that we cannot really win with 2 cops.
Yeah, that does seem to be the case. So in a lot of the times, what you get is something that reduces to like oops, a 5 click that then has like a few edges inside of it. So like if we snip like that and that, you'll notice that there's still a 5 click between like 0, 6, 2, 3, and 5, and the robber will connect something here and like maintain a 5 click that has a couple of connections to start with. Um, so okay, um, that doesn't tell us the answer though, so I'll go ahead and spoil it. So the robber wins on 7, the cop wins on 6, and the robber wins on 7. For 2 cop. So I guess I'll just go ahead and explain my solution here. Um, unless anybody has any questions before I start. Let me look at my
So
little
the game is positive. You said the robber wins on 6 or 7?
The robber wins on 7. The cop
7,
wins on
okay.
6. Um,
Just a procedural question: is there any reason why the robber should not pick shortest path? Or I guess no. I answered my own question. Never mind.
okay. By shortest path, you mean like just identify the shortest path between the 2 nodes and cut that out.
Shortest, most connected, but that doesn't really mean anything. So it's fine.
Well, I mean, you can of course measure the distance in terms of just edge lengths, but yeah, like I don't think that's necessarily the best way to go about it because like the degree of connectivity is really what you're trying to kind of reduce, whereas like shortness, like you could have like one path where there's like a length 2 connection, but then another path where there's like just enough connections that could possibly be made, uh where like if you snip one right now you can stop connection. I don't know if that made sense, but like
Yeah,
yeah,
it
the
has
greedy
something to do
solution is
with
not
number of
optimal.
paths and
Yeah.
some other nonsense. Who knows?
um okay,
Yeah.
so
So from
um
the paper, we have like we have bounds of like 6 and 9 for when the robber starts winning, assuming the cop goes first. Cops go
yeah,
first.
cops do go first, because otherwise like you can't delete the edge from 0 to 1, so it's a silly game
So
anyway.
whatever the answer is, we already knew it was between 6 and 9.
Right, yeah, the math is like figuring out exactly what the bounds are because the upper bound is quadratic. It's like 2n squared plus n plus 1. So as graphs get bigger and bigger and bigger, that's a humongous graph. I mean, as the number of cops get bigger, graphs just get huge. So it's about seeing. And then the conjecture was whether the upper bound is actually linear, which I think 7 shows, right? Because 2 times 2 is 4. Was it 2
Well, I
squared?
mean,
So it's up to 2n plus
no
1.
particular number is going to show us whether or not it grows linearly in the
Right,
long
right,
run.
right.
Yeah.
I know the thing is like I'm just trying to wonder how I might look at like how Alfred Lehman proved this Shannon switching game, like the 1 versus 1. case, he used matroids, but it's not really an area of math I'm too familiar with. So I wonder if that's the approach. It's like you find a way to generalize some lower dimension space on the graphs and prove it that way. I don't know.
Metroids are so fascinating, though. Like, I have been trying to get into it. They're really
Yeah.
fascinating.
Okay, I'm gonna explain how I solved the problem. So stop me at any point here. So I mentioned I'm heavily using bitboards. I gave a talk on bitboards already. Just the very quick summary of how they work is as follows. So an integer on like just a typical integer can be written in binary, and each of those binary digits can be used to store a different piece of information. Um, so for example, in this case, what I'm using bitboards for is I have a struct like a C++ struct called game state, and this represents the state of the graph at any given time. And inside of it, I have two bitboards, one for the cop and one for the robber. So in our game, um, you can think of the cop and robber as removing and coloring edges as we've been sort of doing, but instead, if you think of it as uh, like the cop is painting them one color, which is just black or something, and the robber is painting them a different color, which is red, then you can really imagine it as just both players are just inducing edges into sets, and the cop has their set of edges that they're holding onto, and the robber has their own set of edges. So each of these bitboards represents a set of edges, basically. That's what I'm using bitboards to do. Um, so these are independent sets, so you have to keep them differently in two different bitboards. Uh, does that make sense? I'll explain how I'm actually laying the bitboard out in a moment, but you can just imagine that I'm keeping this bitboard, which I've defined up at the top as a uint64, so a 64-bit integer, um, and I'm using that bitboard to hold a list of edges. I'll take the silence as an understood, and
Yeah, I'm just heading down what you're saying. Yeah, that does make sense.
yeah. So specifically here, let me just add a little something here and like just drop something in the main file. So I'm gonna say make what is it? Print board. Let me just print a print. Is it graph? Print graph? Yeah. Okay. Yeah. So let me just yeah, I'll try this. Okay, so like this is an example of one of my bitboards, and the way that I've sort of been imagining it graphically is that it's basically an adjacency matrix. So like this would be an edge between 0 and 0. So bottom left is uh like the 0 node. So this is like things that are connected to the 0 node, and this is things that are connected. This is also things that are connected to the 0 node. It should be symmetric up to like
It's
transposition
very
along.
vindicating to see it done this way, because I remember when I first came across this problem, first year, I thought of this like I thought to represent this compute program would have to be an adjacency matrix. So it's nice to see this actually was the best way to do it.
Yeah, yeah. So, um, I'll skip to kind of the point of why I use bitboards because, like, a lot of the speed up of doing this all is it just comes down to like copying data structures and like just manipulating graphs in ways that don't involve any search or anything. It's just like, oh, add this edge, and how long does that take? How much time does that take? You want to make that as fast as possible. So that's why I'm using bitboards here. And when you're storing a graph as just an integer, then like you can copy it basically instantly, compared to some like data structure that's stored on a heap. So that's why I'm using bitboards. It's very fast. Um, but yeah, like you can imagine, what happens if I make like a graph on the heap. So if I just make a bunch of nodes that are somewhere in memory on my computer, and then they each point to each other, copying that whole structure would involve basically a flood search algorithm of its own. You would have to go through the graph and like follow edges and copy them each individually. Whereas this is like literally just copying an integer, which is probably like one CPU instruction. If it's like already in your register, it depends on what's already in your registers or what, but like basically one CPU instruction. So, okay, so like for example, this would be used to indicate if this is one, that means that there's an edge between the 0 and 1 node. Now I just made this bitboard randomly, so this wouldn't actually be like a real bitboard because like it's not symmetrical. It should be symmetrical. So here I'll go ahead and make it symmetrical. Um, maybe like 0 1 0 0 0 0 1. If I'm not mistaken, I think it should be that. Yeah, okay. So this is like a real bitboard in which like every node has the 0 node has an edge to all other nodes, including itself. It has a self edge. And which we don't play with. We don't use them because they're not really useful. But and then no other edge has connections to any others. So it's just an adjacency matrix. Nothing crazy going on here. Okay, so that's the way that I'm representing the graph with an integer. Now I guess I'll just go ahead and start explaining my little helper functions here. So we have an add edge function, which given a bitboard, we want to add an edge for like a node U and a node V. So like let's say we took this bitboard and like we wanted to add an edge between like let's say node 3 and nodes 5, for example. So I'll just make a 0-bit board and I'll say add edge 0, what did I say, 3 and 5. And we'll print that graph. And oops, what did I do wrong? Sorry, I have to say 0 0 equals add edge 0. Okay, so now you can see that there's this edge between node 3 and node 5, and you can count and make sure that those are actually 3 and 5, but they should be. So that's what we're doing with add edge. It just adds the edge, and all we're doing here is we take a 1. You'll see that this is split up into like there's this left half and there's this right half. That's because the adjacency matrix has like duplicate connections here. And like so for the left half we just like we add a 1 and just shift it over U times 8 plus V bits, and you can work out that geometrically that just works out to one of these positions, and the other one works out to the other position. And remove edge does the exact same thing, but it just removes that edge from the bitboard. Print graph, I just have loops because this isn't like core to any utility that I'm using for search, so there's no reason to do like fancy bitboard operations. So I just have like a loop based print thing. As edge is just doing basically the same logic here, but it's just checking if there's an edge present. So that's all the boring stuff. So now the question is, how do you check for connectivity on a graph like this, like quickly? Because again, one benefit of using bitboards is that we can copy and manipulate the data structure easily, but we also want to be able to do the operations that are relevant to us quickly on it. And by quickly, we usually mean without using loops. So how do we do that? How do we like quickly determine if like the 0 and 1 node are connected on this structure? So I'll maybe I won't spoil anything. Anybody have any ideas?
Wait, is it okay to have
Well,
loops? Oh, like
oh no, go ahead.
oh,
Well, okay, tell me.
oh.
Yeah, how would
Well,
you?
if it's like O of n versus O of n squared, like
What is n? The number of nodes or the number of edges, or
The number of like in this number of nodes in this case it would be 8. Like I feel like there's no way to do it faster than
tell us your
then.
solution, and we'll
Oh,
maybe
I don't know if I
run it.
have a solution, but
Okay.
okay, I guess I don't have a solution yet. I mean,
Okay.
I know how I could do it if like speed didn't matter, but I think that we are thinking about speed right now.
We are thinking about speed. Like, so the naive solution would be, okay, like let's just work outwards from 0. And let's say, like, we check for all of the um we check for all of the edges that are incident with 0. So like let's say here, maybe I'll give an example here. Let me add a couple nodes to or a couple edges. Let's say 0 connects to 1. Oops. Let's say 0 connects to 1. And let's say 1 connects to, ooh, wait, sorry, we don't want that. 2 connects to 3. 3 connects to, maybe 1 connects to 5. So this is just like a path, basically, this graph that I've made. Okay, so this is what the bitboard looks like. So you'll see 0 is incident with 3. 3 is then incident with 5. Because there's this 1 that indicates like this is on the coordinates 3 comma 5. This one's on the coordinates 3 comma 1. And this one's on, or sorry, 3 comma 0. I mean, this one's on the coordinates 1 comma 5. So what you'll notice geometrically is that like starting in row 0, we can sort of trace horizontally to a 1, trace vertically to another 1, trace horizontally to this one, and now we've gotten to a column that is index 1. Does that make sense? Another way of framing this, I kind of cut to the punch a little bit there. That's how we're going to do this with bitboards. But another more simple way of thinking about this is just like check for like maybe make a set up front of all of the nodes that you've induced into your into your connected to 0 set. So start with 0, add it to that set, and then just continue popping things from the top of out of that set and check for any other node that is incident with it. So just find all nodes that are connected to 0, add them all to the set, and then continually pop them from the set, and then check what's incident with them. And you inductively pull new nodes into this set if they're connected to 0 or something that it's already touching. And then if you ever get 1 inside of that set, you know that 0 and 1 are touching. Did that make sense? That was a lot real fast.
So basically, you use the index of the, you use the bits which are set in the corresponding row for a given node,
Yeah.
and then you basically rotate it, and then or over those bits. Yes.
Rotate it. So, sorry, you rotate
So
it and then what?
basically, you want to check if is it connection from 0 to 1, right? You have
Mhm.
this path that you trace over basically this 3-0 up and then left and then up again.
Yeah. So
Okay.
that's the bitboardy solution. Is we're starting at 0 here. We can move over to the right, then up to this one, then left to this one, and now we've landed on column 1, meaning we've got node 1 in our activity graph. That's the
Is
that's
it
the
is it appropriate to think of it like, or am I misunderstanding? Because when I think of an adjacency matrix, I can imagine like, let's say we had another row at the top telling us that's nodes 1, 2, 3, all the way to 8, and then the same thing, another column on the very left. So you can see like column row. Let me see if I can look here. So row is that 1, 2, 3, 4, 5.
FYI, this is
So
0 indexed. Like the left is 0 and the bottom is 0 because I have a node 0 in my graph.
oh, okay. So I guess you just shift everything one up,
Yeah.
one to the right. Yeah.
Yep.
Or well, yeah. But that's kind of the idea. So like, I'd look at, I guess that, So let's say you can move your mouse like to the very top, but this but one down.
One down. Okay, this one.
One to the right of that.
Okay.
So that would be like 1-1, pretty much. And there's
Zero
no.
zero is the bottom left. So 1-1 would be
Oh,
here.
sorry. Be here. Okay,
That's
it's the other
just-
way around. Gotcha.
I'm just representing it that way so that it's like a
Yeah,
coordinate
yeah.
grid.
Okay.
So this
Cool.
would be
Okay,
like
I got it.
1,7. This would indicate that there's an edge between, or sorry, 1,6.
Yeah.
This would indicate there's an edge between 1 and 6.
Gotcha.
Yeah. So
basically, you're just bit unioning over the non-zero rows as a result of the AND operation over the existing set that you've already collected, right?
I think that was right. Your bit. Say that one more time.
You are making this union a 8-bit wide set that you use bit union over for like set membership. So or right as selected by the rows which are non-zero over and of the existing set.
I think that's correct. I'm slightly lost on your wording there, but I think
sorry.
it sounds like the right idea.
Really bit or like bit magic.
Yeah. Yep. Yeah. So okay, let's see. How did I actually do this? I'll walk you through my little solution. Where the heck is it? Okay. Yeah. Is 0, 1 connected? So this is like the big function that we really care about, that we're going to be calling all the time. So it better do something fast, right? Let me get all that gunk out of there. So it calls these two functions a lot: make row stripes and make column stripes. So I'll first explain what those are doing. Make row stripes is like a function that will, if there is a 1 in the row, it will turn the entire row into ones. So I'll go ahead and just so that you can see, I'll pop that out. I'll print graph 0, print graph, yeah, make row stripes of 0, print graph, we'll make column stripes of 0. And okay, so this is our original graph. This is with the row stripes of our graph. So you can see like this row had a 1 in it. It had more than ones in it, as a matter of fact, but that doesn't matter. So the entire row gets transformed into ones. This row has no ones in it, so we continue with no ones, and so on and so forth. And you get all of the rows that have ones in it are the one is flushed out across the row. Column stripes does the exact same thing, just vertically. I think someone said rotation earlier. Rotation, as far as I'm aware, is not really fast. There's no fast way to do rotation, at least on an 8x8 bitboard. So we don't do rotation and then the same operation. Like we can't reuse the same function for both of these utilities, even though it's kind of symmetrical. If you imagine we did have a rotation operator, it might be sensible to call rotate, then make row stripes, then unrotate, and that would be a way to do column stripes. We don't do that though, because as far as I'm aware, there's no quick way to rotate. Okay, so how are we doing this? To make row stripes, actually, this is the harder one, I think, of the two. I'll start with make column stripes. So make column stripes, basically, if you right shift 8, that corresponds to shifting down 1. If you left shift 8, that corresponds to shifting up 1, right? So you can imagine I copy this bitboard, paste it, just shifted up by 1 spot, and then paste it shifted down by 1 spot, where we're pasting ones anywhere. And since we're using ors all over the place here, like if 2 ones like land on top of each other, that's fine. It's just still a 1. So think of it like we're picking up the ones and copying and pasting them vertically. We go right 1 and then left 1, then right 2, up 1 and then down 1, then up 2 and then down 2, and then up 4 and then down 4. And you can play that out in your head and figure out that should indeed cover all of these, like the total row as necessary. Does that make sense?
Yep. So
Cool.
this is like what you do when you're bit counting and stuff.
Right.
Yeah.
Yeah. Okay, make row stripes is a little bit harder. Can anyone tell me why you can't just naively do the same thing except divide all of these numbers by 8 and do like BB or equals BB left shift 1 and right shift 1?
Because left shift 1 could make it go around wrap another row.
Yeah,
Right
yeah,
shift
you
1 too,
bleed
yeah.
between rows. In this case here, you're not actually bleeding like outside of the like it just goes into integer overflow. Like some of these ones get pasted outside of bounds of the integer. Like if you take something in position like I don't know, bit position like 40 and then left shift at 32, it's now outside of the envelope of a 64-bit integer. So you don't have to worry about that in the column case. In the row case, if we take like a bit that's here and then left shift it 1, it like sorry, I don't know why that won't highlight. If you take this bit and like I think actually it's right shift it by 1, it would end up here. So you can like transfer between rows, which is not fun. So how do we deal with that? What I'm now doing is we basically do half of this operation where we right shift like 8, 16, 32, but instead we right shift it by 1, 2, and 4. So we are going to blur it rightwards over the next like seven spaces so that it will occupy a row of 8. But then you can how do I say this? You can only check the leftmost position in that slurred together set. And if that one is a did I say that right? Yeah, if
Oh, wait,
that
just
one
to
is
be
a
clear,
yeah,
bit shift right is making it go left in the
that's
diagram
correct.
here, right?
Yes, that is
Because yeah, the
correct.
left side is the least significant bit.
That's correct. Yeah. And good call out. So like by shifting like by bit shifting right, we're shifting the one left. So let's just imagine what that looks like. If we shift this one left by 1, now we have 2 ones here. Now we're copying and pasting those 2 ones left like shifted geometrically leftwards by 2. So these 2 now. And then we shift those 4 ones that are here to cover these 4. You'll notice that now this spot right here where there's a 0. By the way, you guys can see my mouse, right?
Yeah.
Okay, good. So that will cover this one, or so this bit with a 1. And that's basically the check that we're going to use to see if the entire row is covered. If this leftmost column has a 1 in it, that means somewhere in that column there was a 1 before. So that's what we're doing with this little magic number here. We OR it with the bitboard, or sorry, we AND it with the bitboard that has the entire left column covered. So that just basically isolates only this leftmost column. We throw out everything else, make it all zeros. And then we multiply it by 0x which is like just a single row, like the bottom row. So if you can imagine, if you multiply just 1 by 0x you get ff, which is the bottom row. If you multiply like this bit by ff, you get this whole row. Have I lost you guys?
You've not lost me, but you make me feel like there's a SimD solution here that's just screaming
I'm
for
following
attention.
the
Maybe.
bitboard rotation, but I forget. I guess getting lost in details. I forget. Just to clarify to make sure I'm following, you store a bitboard for every. So as the game goes on and each player makes a move, it essentially creates a new bitboard as it's transformed. So you kind of store. I guess, like you said, you treat them as a bitboard is an integer, so you treat them as just integer added into the set for each player as the game goes on, right?
Bitboard is not being added into the set. The bitboard is the set.
Oh, right. Okay.
So like this is like you
was-
can imagine this is the cop's set of node or set of edges right now. Like the cop owns the edge. like 0, 3, 3, 5, 5, 1. That's the set of the cop's edges. So that way we don't have to contain an unknown number of bitboards. Like you could split this up into 3 different bitboards where each one is one edge. But that would be silly because then you have to loop over the amount of edges that a player has induced into their
So
set so far.
they're 2 bitboards, one for the cop, one for the robber.
Yeah, correct.
Gotcha. And it's transformed. I mean, the transformation pretty much is the act of deleting or claiming an edge.
Right. Yeah. So we transform these by just adding a pair, like a transpositionally symmetric pair of these 2 ones. That's how you would add an edge to the player's set.
Gotcha.
Okay, so is 0, 1 connected? So we can take for granted that these functions work now. How do we check if we've connected the 0 and 1 nodes? Okay, so first thing we do is we want to basically the idea is we're gonna inductively loop between these 2 things to include nodes in our set of flood search basically. I'm actually gonna go ahead and print. I'm gonna go ahead and print out everything actually because I think that might make it easier to understand more so than I ever could explain. Let's say print graph. Oops, let's frontier. Oops. Sorry, I'm failing my Vim test. Oops. Print page frontier. We'll also print S frontier and graph. Okay. Let's try this real fast. Now, if I go to the bottom and say, is 0, 1 connected of our graph? Okay, so this is just all of the processing that it's been doing that it did to figure out if it's connected. And as we know, it is connected, right? So ignore these 3. These are my print statements from before. Get rid of those actually. What happened? Okay. So in our algorithm, 0, 1 connected. So the first thing that we're printing here is the input graph. So like this chunk here is this is what we put in. Now the first thing we do is we AND that with ff, like just 0xff. So a single full row. So we're ANDing it with this bottom row. So that means everything above that gets discarded, and we're just left with the 1 on the bottom, like this. So then we enter this loop. We print what's sorry, we printed this. That's what we just printed. Now we find S frontier, which is the column, like the stripy column version of this thing. So that will look like this vertical line. Then what we do is we AND that vertical line with the board that we had to start with. So now these 2 ones are in that board. So we now have like that one and that one inside of our set. Now we do the same thing, but this time like horizontally. We stripe those out in the horizontal direction. And then we AND that with our board again, and you'll notice that this one now got added to our list. So this is basically following this sort of geometric intuition of forming a path that I was describing just a moment ago. You start with the 0, which we're doing by starting with the bottom row. Find any 1s on it, and see if they connect to any other like edges. Effectively, if 2 1s are in the same row, that means that the edges are incident through an edge, or sorry, through a node. So this is one edge and this is one edge, but they both touch node 3, right? Because this is like 0, 1, 2, 3. They both touch node 3, so that means that they can be connected into a path. And so we can just do this like loopy, like following a path direction thing to find like a path from 0 to 1, and that's all I'm automating here. So we find these horizontal stripes, and that lets us induce this one into our graph. Then we find vertical stripes, and we just continue doing that. And eventually, you'll notice that like this thing here is the same as this thing here. So after that means we did a whole iteration of like making stripes and inducing things into our path, and nothing changed. So we break out because this bitboard is the same as this bitboard. So that whole process you can see pretty clearly in the code over here.
So, quick
I have to ask a
optimization
quick question. I have to.
Go ahead.
I'm sorry. Sorry, I have
Please.
to run really quickly. So make sure I'm following. You start with a row, like that zero row.
Yeah.
You run along there and see if there's a 1, and then you kind of run up the column and see if there's a 1 along that column. Right?
Yeah.
So say
Exactly.
you find that 1 in that column, where does the striping come in? Like, what is the next step from there?
You just repeat the striping, but this time you have that new 1 inside of your bitboard.
Right.
So like we started by only striping the bottom row, and then
Oh, wait, so
striping.
if you detect a 1 in a row, the entire row becomes 1s.
Yeah, and then you and it with the original graph.
Okay, then you and it meaning that adds to the
No,
the
no,
graph?
no, no. That means it intersects, like bitwise and, as in like 0 and 1 is 0. So like what I did here between these two, what's happening is it's running bitwise and between this stripy graph and the original graph. So you'll see that all of the stuff that didn't have an edge to begin with, and also doesn't have an edge in this stripy graph, will come out to be 0. So, and that's true. All we got here was just the ones that are inside of these two columns. So that is the way that we're mechanically figuring out what can be added to our adjacency matrix. Effectively, just performing search, like sort of doing that like inductively pulling in new edges into our list of touched edges, and like thereby sort of doing that, performing that search outwards, but much faster.
And it stops itself once you, let's say we found in that bottom row, we found that 1, went up the column, and then we found another 1, but then it as it shifted itself over and it went up again, it couldn't find another 1, then it stops.
Exactly. Yeah, it stops as soon as continuing this stripy procedure stops finding new, like if you run one iteration of this like horizontal then or vertical and then horizontal stripes, and nothing new is found, then you know that repeating it again won't find anything else ever. So you can just terminate there. So that's what this line is doing. We say like after we've done one iteration is like the new frontier equal to the previous one. Then like if it's the same thing, if you didn't find anything new this iteration, then you just stop. Otherwise, you set it equal to itself and then run the loop again and continue to find new edges.
And this process is literally just checking the game state, like is 1 and 0 connected?
Yeah, this is how we're quickly determining if 0 and 1 are connected. And then like to actually answer the question of are 0 and 1 connected, given all of this stuff that we've done, we just figure out if like anything on the one row is 1, or anything on the one column is 1.
I have 2 optimization questions.
Yes.
Is the break actually less expensive than a fixed length for loop? And is that will a fixed length for loop with a forced unroll not be faster in this case? Because basically you're asking the speculative execution in your CPU to just scream while it's trying to figure out, okay, am I quitting here or not?
Yeah. Yes, that's a good point. The honest answer is I I answered the problem, I solved the problem, and then stopped thinking about it. Um, so there's definitely a possibility that you're right. One thing to note though is I did make this program for up to like it works up to graphs of size 8. So like if you were to do that, even if you were to play like on a board of size 4, which is implicitly defined within this bitboard, um it would still be using an envelope of size 8, and you would have to unroll your loop to support 8. Or at least 7, because that's the solution to the problem that we care about. So
Yeah, that's fine.
maybe my intuition says the break is probably worth it here, even though, like, yeah, even though you might be wasting a bit of time,
I hope
with
you've
your jumps and
understand that
whatnot.
you've nerd sniped me now. You know, I have to figure this out.
Okay. Well, the code's all open source. Um, so go ahead, feel free. One thing I actually just noticed right now is this return could actually be inside the loop. Um, you could go ahead and just like say if that's true up here, then you can just return out, and that might actually like shrink your search time by quite a bit. Um, like that might I think maybe best case that might have the amount of time that you spent inside
Yeah,
this function.
I think the optimizer will do that for you.
Really? That
Yeah,
surprises me.
because you have a break directly into return. It's definitely inlining that for you.
No. I don't mean inside of the if statement. I mean above the if statement. So, like if I think I can here. Let me just go ahead and I don't want to do it on the fly. But like the idea is if either of these are the case here, then we don't have to continue doing flood search in our graph. Like we already have found a connection between 0 to 1, so we've already answered the question that this function actually cares about. Whereas
I believe that will just return false before continuing
yeah,
the loop.
yes. That's why I said I didn't want to actually implement it.
Oh, yeah.
But like it would be something along the lines of, and I don't guarantee this is right because I'm just thinking on the fly here. Like if this or is true, then we return true. Yeah, like this. And then maybe if we, I don't know, if we get out, then we just
Yeah,
return
I
false or
think the
something like that.
optimizer would still pick this up because that while true would be undefined behavior if it doesn't terminate. So it'll optimize that. Trust the LLVM. It'll handle it.
Wait. No, I don't think you're right. Say that again. If
So while true is
yeah,
like an infinite loop is undefined behavior, so it knows that it
yeah,
won't happen.
sure.
So the optimizer will do shenanigans to basically assert that eventually that break will happen, which means that the loop condition will be moved and then it will eventually inline that return. I'm telling you, man, the optimizer does some insane shit. Like,
No, but how would it know? Yeah, but it wouldn't have the speed up still because it doesn't know that like the goal of the function is to return these two things unless it somehow like figures that out by like you see that maybe it's not clear, but I'm suggesting having both the break here and this check.
yes, I understand. My point is that because it knows that the loop terminates,
Yeah.
it also knows that eventually that return gets hit. It knows that that
Which
boolean,
return? This return or this return?
this outward return, because it knows that the outside return gets hit,
Yeah.
and it knows that you're trying to return a boolean, or rather a return of a value based on this.
Yeah.
I'm pretty confident that the optimizer would pick up on the fact that you could return early here, but I'm
Huh.
it
If that's
probably
the case,
will
I would be
off
very
mark.
surprised. In fact, maybe after this talk is over, I'm gonna rerun my solution. It took like maybe an hour or so, but maybe not. Maybe like I don't know, something on that order of magnitude.
Yeah,
Probably less, I think.
it definitely put this in Godbolt and see
Yeah,
what the optimizer does with it.
yeah. Anyway, beside the point. This could definitely be optimized more. I didn't make it like bulletproof, super fast. It's just good enough to solve the problem. Um, uh, Okay, so that's the fundamental idea. Did robber win is just like, is 0, 1 connected on the robber graph? Did cop win? You just check all of the nodes that the cop doesn't have, and so like you're turning all the zeros to ones and ones to zeros in the cop's graph, um, and that checks if you've already disconnected 0 and 1. Is move legal? This is just checking, like, for a game state that has both the like a cop and a robber, you don't want that node to already be in either of the two of their bitboards before you make a move. And then after that, it's just like typical recursive minimax style algorithm here. Um, this is incredibly ugly. This cops turn evaluate. I literally just copy and pasted it for like 3 different options of how many number of cops there are. Don't do this at home. This is terrible practice. I was lazy and in a pinch of time. I just did that. You could do this recursively in a way that's probably much nicer. Um, anyway, you can basically just focus on this chunk here. We just iterate over like two nodes to pick an edge from. If that is a legal move for the top to remove the edge, then we basically do exactly that, and then we just like do a dual recursion call for this function, robber's turn evaluate. And then the robber adds the like attempts adding edges, and through dual recursion we just do search, like a typical minimax type search. Um, and I just got a whole bunch of unit tests. Um, and yeah, this is just UI stuff down here, basically, like playing against the computer versus like actually trying to evaluate things and stuff like that. So that's my solution. I think, let me go back to event announcements. What did I want to talk about? How could this further be optimized? Um, so I was actually expecting to need to do more than just this to solve the problem, because I don't know, I figured someone would have tried something like this already, or something comparably fast. So I was expecting to actually have to implement some sort of either symmetry detection or canonicalization. Um, what canonicalization is in a nutshell is like, let's go back to here, let me go back to my little this thing. So in this case, like deleting an edge between, well, we have to delete an edge between 0 and 1, but now at this point, all other nodes are functionally equivalent in the sense that their set of edges is like symmetrical between them. So for example, like deleting the edge between 6 and 2 is the same as deleting the edge between 5 and 2. My program doesn't know that. So like there are two sort of ways to solve this. I guess the sort of slightly more naive and not quite as good approach is detecting symmetries between edges, or sorry, between nodes. Um, so like in this case, we could have it figure out that all of these nodes are functionally the same, and also it would determine that there's a symmetry between 0 and 1, and those could be interchanged. And that way, like an edge between 0 and 2 is the same as an edge between 1 and 6 for our concerns, as the cop. So you could do that and then reduce it to only do one move out of the set of all outgoing edges from 0 and all outgoing edges from 1. A sort of more clever way of doing this is what's called canonicalization, which is where you basically define a canonical form for a graph. So suppose we have like, how do I want to explain this? Suppose we have we could imagine all of the graphs that we get by snipping one edge off of this. Then we can canonicalize it by uh, basically exchanging numbers between these, such that some kind of property is held. For example, um, maybe like it's in ascending order of uh, of edge degree between the nodes. So like 0 has the most outgoing or the least outgoing nodes, then 1 has the next least outgoing nodes, or something like that. If you can sort these things in a way that there's a unique definition of them, then you can canonicalize your graph and like hash the solution that you get for one graph and another graph that has the same canonical form, meaning that it is like functionally for us the same. So that would be one. That's like the next thing that I was planning on doing. That and memoization, like just remembering answers to subcalls of the function that like the search function that I had. Although I never needed to implement either of those. It worked good enough just as is. Um, so I didn't actually get around to doing that. Also, canonicalization on graphs is hard. I'm not sure how I would actually implement that. So I'm glad I didn't need to. Any questions on that before I continue?
Well, I guess one question I have is like, what do you estimate the speed up would be if you implemented those features? Like, I
Like
imagine
a lot.
because I'm imagining like for the first operation, it's already like 7-fold increase from the symmetries,
Right.
and then like I guess the further you get, the less symmetries there will be. But already we're times 7. So
Yeah.
then it's
It's a
even more
lot.
than yeah. It would probably be like the difference of like hours to seconds or something.
Yes, it very well might be on that level. It would speed it up a
I
lot.
think, yeah, memoization is really interesting in this problem because, well, memoization is, well, in essence, you write the answers as you go and you reuse them later, right?
Yeah.
So for example, up to n equals 7, you can memorize the connectivity of a graph as a number. So what I mean by that is like you pre-calculate all the graphs beforehand and calculate whether 0 is connected to 1
Yeah.
beforehand. If there are 7 nodes, there are 21 edges. So there are 2 to the 21 possible graphs, which is like 2
Right.
million. And you can store 2 million values beforehand.
Yeah.
Now, but this is not enough to solve the entire problem by memoization because in the actual problem, each edge can have 3 states that they can be like not
Yes.
yet touched by either a cop or a robber. They could be like colored by a robber, or they could be removed by a cop. So that's 3 possibilities for every edge.
Yep.
So there's 3 to the 21, which is a lot of possibilities for a graph. But yeah, I think it's an interesting question whether that can be reduced enough to the millions or something through
I
like
think
using symmetry.
I think the answer is yes. Oh yeah, exactly. So that's the kicker there is like once you canonicalize, then you have much less like um symmetrical classes of graphs that you have to memorize over. Um yeah, so that was going to be my answer to your question, but it seems you got there before
Oh,
me.
yeah,
So
yeah.
yeah, I my hunch is that yeah, it would be tractable if you if you are able to completely uh like make a full how would you word it? Like if you can identify all symmetries and canonicalize them all and make all genuine classes of oh it's the same graph actually represented the same way. I think the answer is yes. That's entirely intuition though. I don't have any proof for any justification for that. Just by having played a couple of times, I would even go so far as to say maybe even like with a graph up to like size 9, that might still be doable.
Yeah, that's really interesting. Maybe someone will do it after seeing the YouTube video.
I hope so. That would be cool.
Wait, are you making a YouTube video of this?
Just the recording of the talk.
Oh, all right. Hello, YouTube audience. Wait, one thing I was thinking though was like you were talking about graph of size 9.
Yeah,
If that were to happen though,
yeah. The
how would your
bitboards don't work
Bitboard?
anymore.
Yeah,
Yeah,
I was gonna say like, would you have to go up to like 2 bytes? It
yeah,
would get really messy.
yeah. Well, so you can do this with like two 64-bit integers, or you can just use a 128-bit computer. Like
Oh
that's a
yeah,
thing you can do. But
that would
Yeah,
just
don't
Yeah,
worry
or
about it. I got one of those lying
like
around.
the hardware
right,
will
right.
catch up to you.
yeah, exactly.
You can also like reduce the number of bits to 2 if you like, right? Because technically you only need the number of edges amount of bits. So
Yeah,
it will be harder to implement, but I guess
there
it's
are
possible.
ways. Um, I think this is what you're saying. There are ways that you can optimize for the amount of bits in here that you're actually using. For example, I'm making no use of the diagonal anywhere as an obvious example because we never care about edges being self-incident. So, or sorry, nodes being self-incident. So, like, this diagonal is completely meaningless and wasted space in our use case. But furthermore, there's also just the entire triangle, like the upper half, which is symmetrical to the bottom half, and for that reason, we also don't care about it. Now, I'll note that in my flood search here, where we do the like verticals and horizontals and stuff, I make heavy use of that. So I'm depending on the fact that this is symmetrical. It would not work correctly if you were to like zeroize one section of them. So you would probably have to rewrite that, and I'm not sure off the top of my head how that would look, or if it would be as fast. I think probably, but not sure. But that is one way to recover more than half of the space inside of one of these bitboards. So
mean-
at the cost of maybe some slowness and some ugly implementation details, it's probably workable to do 9 within an 8x8 bitboard.
The good news is that you've accidentally also made a solver for a directional version of this game.
That's true. Yeah. Although I guess it would be like a cop deletes one directed edge. Yeah, I'm trying to imagine what playing that would look like. I guess like yeah, the cop can delete a single direction of an edge at any time. And
A
the
new
robber can only
unsolved problem was just unveiled.
yeah, yeah. Yep. Although
Also, for the optimization questions about larger matrices, like when we do use adjacency matrix representations or like directed graphs, like
Yeah.
SIMD is the answer. I mean, you can always get away with the really big, like what's the word for that? My brain immediately forgot the word for this, but yeah, we have ways to optimize really big bit operations like that.
Sorry, big bit optimizations for what exactly? Or
For large adjacency matrices. Like
that are stored in bitboards or that are just stored as
I mean,
matrices?
they are stored as bitboards, right?
Yeah. I'm just making sure you're not saying like in a world where we implement this with arrays or something.
Oh yeah, no. I mean
Okay.
they are arrays, just arrays of bits.
Yeah.
But yeah.
Wait. I'm missing what you're saying. You're saying SIMD can be used to do what precisely?
SIMD can be used to expand these to 64 by 64 very easily.
I see.
And
Yeah, that makes sense.
even larger
Yeah.
sets as well.
Yeah. Okay. Yeah, that makes sense. For anyone who doesn't know, Addison probably knows more about this than I do. But SIMD is like you can tell the CPU to do this. It stands for same instruction, multiple data. So you can basically tell your CPU to do like the same thing to 4 different, I don't know, to some number of different bits of data, pieces of data. In this case, I think what Addison is suggesting is if we wanted maybe a bigger envelope than our bitboard can provide, we could maybe just imagine stitching 4 of them together and then simultaneously run whatever sort of instructions we're trying to run on all 4 of them via SIMD. Correct me if I'm getting that wrong.
Exactly correct. I mean, it's what my original thought about this is that
Yeah.
like there should be a way to do this kind of rotational stuff more easily.
Yeah.
Like
Maybe.
it feels like there should be something there, but I don't see
Maybe.
it.
One other thing that comes to mind, maybe you realize this, but like, if we're using SIMD, like, you can't just use SIMD alone to do like making, for example, making a stripe on that 4x4, or sorry, 2x2 box of 4 8x8 bitboards. Because like you would then have to OR the top bitboard with the bottom one, like against the bottom one as well, right? As well as with itself. So like I think you would just get linear scaling instead of quadratic scaling of runtime. If
Yeah,
I'm
eventually you'd run out,
okay.
but
Yeah. Okay.
You can get really far before then. I think the largest lane is 256 bits, so you can go a long way.
Oh, okay. That's interesting. Wait, maybe. Okay, I might just be at the end of my understanding here because I think you might be saying something that I was assuming was impossible. Like you can simulate. It sounds like you're saying you can just natively simulate an operation on a higher size integer.
Yeah, as far as I understand, you can get a SIMD instruction to do a 256
Huh.
wide integer and then multiple times.
That's cool. Okay. Yeah. Okay. Then I was wrong. Then I think what I was saying here of you needing to like. I mean, maybe after some bound after you hit that 256 limit or something, then you start to have to do fancy stuff.
Yeah,
But
I think you have other theoretical limitations before that.
yeah, probably. So I think yeah, maybe if someone were to like implement canonicalization, were to pack data more efficiently, um, or use SIMD, or maybe put this on a graphics card or something, you could probably solve the n=3 case, um, like for 3 cops. I think that's really all I had. Any questions? This already went way longer than I expected.
So I looked up a bunch of some of the relevant math results. Is now a good time for that, or maybe if people have
Yeah,
questions first?
absolutely. Yeah. Well, yeah, sure. Does anybody? I mean, is that going to be a whole tangent? Any
No,
questions before that? All right, floor is yours.
I just three quick things. First, I misspoke about the Kimberly Wood paper. The known bounds were 6 and 11 for when the robber starts winning.
Hmm.
But Kimberly conjectured that 9 would be enough, and in fact, you just learned that even less is enough.
Mhm.
And then for 3, since you were talking about someone doing 3, the bounds are 7 and 22. We'll see
Yeah.
where inside that lies if someone writes the code.
I tried playing on this thing a little bit with 3, and I couldn't beat it with was it 9? Maybe it was 9, maybe it was 8. I definitely couldn't beat it with 8
Okay.
as me playing as the robber. The cops seemed to win at 8, but,
Yeah.
you know.
And then the two things that seemed kind of relevant. There's there's an old paper called "Remarks on Positional Games 1," and this is about a very, very general class of games. So in the previous talk, there was some mention of make or breaker games. So basically, in this game, in this Shannon switching game, we have the robber is trying to make basically any path between 0 and 1, and the
Mhm.
cops are trying to stop that from happening.
Yep.
And so you could imagine like any kind of setup on any hypergraph with any like goal shapes for the
Yeah.
quote unquote robber and the cops trying to stop them. And so
Right.
like there were very general bounds in that paper for
That's
that.
very reminiscent of, like, Ramsey theory where you're trying to, like, construct a clique or something.
Yeah. Make or breaker games are closely connected in that
Hmm.
kind of way.
Cool.
But the super general bounds, if I did the calculations correctly, like are not good enough to really say who wins in
Gotcha.
this situation.
Okay.
And then the sort of closest thing, which also doesn't answer this question, I found there's a paper, a much more recent paper that first came out in 2018, uh, Make or Breaker Percolation Games 1, Crossing Grids, and it primarily talks about like instead of a complete graph, like a grid graph, and then this is kind of very
Uh-huh.
similar to like the
Okay.
game
Yeah.
Bridget or Hex or whatever. It
Right,
kind of
right,
has
right.
that
Hex
kind
would
of
be an
flavor.
instantiation of this, yeah.
But in the middle of that paper, they do have like kind of a tangent about general Shannon Switching esque games, but they don't they don't have any results that would apply here. And I think maybe there's like another paper that also talks about if the goal were to make a whole spanning tree to connect everything to everything else, there are like really good bounds known about that problem, but that's not this problem.
Interesting. I get.
Is
Yeah.
there any link to the min cut problem, do you think? Like, I feel like there should be a very natural link from this problem to the min cut problem of all the reduced graphs that get generated through this process.
That's a good question. I'm actually just gonna play with this graph a little
I
bit.
don't know. So certainly, like it reminds me of Mincut and MaxFlow, but I don't know if there's any connection to any of these papers. I certainly haven't read all these papers, the other papers, such.
Like that does seem like a naive strategy that I might try and make. Like, is just find the min cut and then cut along it. Like I'm trying to set up here just an example of a simple like graph where the min cut is obvious or something. Let me see. So I
feel
guess
like-
here min cut would be 3.
Right. I feel like min cut is kind of equivalent to like, sometimes when you have an NP problem and a P space problem, you kind of have you kind of have a similar problem where if you play it by yourself, it's an NP complete problem, and if you play it with two people, it's a P space complete problem. There are some problems like that. I think Mincut might be the one-player version of this game, and maybe there's some kind of connection you can make there, like something like that.
Could be. Not sure.
Yeah.
Cool. Any other questions?
Do you think when n increases, the threshold, like where the robber starts winning, goes up like n squared? Like if n were like 100, like let's say the robber places 1 and then the cop cuts out 100. What do you think is the ballpark?
I don't know. I honestly don't know. I'm wrestling in my head. I want to say it might be closer to linear than quadratic. I think it's probably somewhere in between, honestly. I don't know. I don't know though. I don't really have
Oh,
a
yeah.
strong intuition for like I have an intuition for like maybe like the 3 and 4 case, but if we're starting to talk about 100, like I don't even I can't even simulate that in my head.
Oh yeah, I mean I think that like 100 click is like really hard to think about because it's like you can cut like thousands and thousands of edges and
Yeah.
everything is still very well connected.
But you would need much bigger than 100 click for 100 cops because the 100 cops
Oh.
could just separate one immediately on 100 click.
Oh yeah. Yeah, I think linear sounds right because I feel like when you have 200 nodes, you have like like 40,000. I don't know. It's just something
I don't
was
know either.
thinking because like this you have 2 cops and it's like, you could have as many cops as you want, but it gets kind of complicated then.
Yeah,
Yeah,
I mean
I don't know.
certainly the bound, the 2n squared plus n plus 1 bound means that if you have 100 cops, then certainly the robber wins by the time you have 20,101 vertices.
Yeah.
Oh yeah, that's true. Yeah, so at least one of the bounds is like very easy to figure out.
Yeah, I don't know. I don't want to speculate about numbers that I can't put on my fingers. Any other questions? If not, thanks for coming. Hope you enjoyed.
Oh yeah, thanks for giving this presentation.
Absolutely.
Yeah, it was fun.
Cool. Glad you enjoyed.
Thank you. Thank you.
Bye. How do I stop the bot? I forgot.
I have further comments after recording.
1 sec. There we go.